Hi, welcome back. Today's lesson, we will work on efficiently computing the co-movements of multiple variables at the same time. This means we'll be working on multivariate analysis. For this, we shall be using matrices and MS Excel to do these computations, and we'll work directly using matrix notation rather than using the formula approach for the applications, as it would be too cumbersome otherwise. So let's summarize our formulas so far. So when we talk about mean, what we do is we sum up all of the numbers of a variable, then divide by n, which is just the average of the numbers. And when we talk about variance, we sum up all the squared deviations from the mean of a variable, then divide by n. So we're talking about the average of the squared deviations from the mean. Then we also talked about covariance. And here we sum up the co-movement of two variables from their own means. You sum it all up, then divide by n. So this is the average co-movements between two variables relative to their means. Then you have the correlation, which is the standardized version of the covariance that runs between -1 and 1. So the question now is this. Instead of separately taking a look at each individual variable and its statistical summaries, what if we want to come up with a summary of the statistics of a whole portfolio of variables? Meaning, if there were 3 variables, what would be the mean and variance of the aggregated 3 variables taken as a whole? For convenience, we will shift the application to modern portfolio theory for returns and take a look at applications in stock returns. Although the analysis can be clearly extended to any other kind of problems aside from this. So let's start with 2 variables, stock A and stock B. We now consider having a portfolio of the returns of the 2 stocks with weights for each labeled W and given the return and variance of each stock. So the return will be just the weighted average of the 2 stocks. So if we're given this and we're just doing a 50-50% weight for both stocks A and stock B, then what we simply do is just we get the weighted average of the 2 returns. And that's simple and straightforward. What's not simple and what's not straightforward is the portfolio variance, which is quite complicated and requires the pairwise covariance of the variables involved. So here we have only 2, but if we have more variables, then we'll have to take all the kinds of pairs that you can get from all the variables involved. Anyway, the formulas look like this if you're using the covariance. But if we're using the correlations, the formula would look like this. However, as you can imagine, it's really quite cumbersome and tedious to be working with just 2 variables. Imagine if you have 3 variables, 5 variables, 10 variables. For these kinds of problems, really, it's best to work with matrices, in which is the topic of today's lesson. Now, let's call omega the Variance-Covariance Matrix. We've talked about variance before, and we talked about covariance before. Here, we're going to have a matrix which will contain the variance and the covariance. So let R be the return vector, let W be the weight vector, and omega is the variance-covariance matrix. It's very simple to work this in Excel. The portfolio return is simply just weight transpose times the return vector. And the portfolio variance would be weight transpose times omega times weight. That's it. It's quite simple. And just to give you an idea of what kind of computations are required, we'll have this matrices like so. And the solution to get the portfolio return would be this. Then we'll have the portfolio variance like this. So it's pretty straightforward. That's it. It's just a simple matter to compute the portfolio return and variance using the matrices. So with matrices, the computations become very straightforward. And by the way, the actual computations will be demonstrated towards the end of this video to help you double check your work. We highly encourage you to actually open the spreadsheet and work the numbers yourself using Excel. Anyway, meantime, the biggest question might be, what is the variance-covariance matrix and how does one compute for it? Regarding the first question, it's called the Variance-Covariance Matrix because the diagonals are the variances of the different variables involved, and the off-diagonals are actually the covariances of the variable that intersect at a particular cell. Some examples are in order. First, note that if you take the covariance of a variable with itself, it becomes the variance. So for example, here's the equation of the covariance. And if you're taking a look at A versus B and A versus A, then it's just simply the covariance of AA is simply just the variance of A. So if we start putting this thing together, the variance-covariance matrix will have the variances on the diagonal. And then we will have the labels like so. It's like you're gonna try to intersect the labels between the rows and columns like AA, AB, AC, BA, BB, BC, and so on and so forth. And the diagonals would be the variances of A, which is just covariance of AA, covariance BB, and covariance CC, like so. And all the off diagonals will be the covariances between the labels, and we will have this. Note that we are always talking about the mean adjusted values here, as we are talking about cove movements. So to start computing for this, let's work on the original data set, which we label as matrix X, and let's call matrix X adjusted as the matrix after adjusting all the data by their own means, meaning we create a new data set where we subtract the variable's mean from all the other numbers of that variable, and we do that for all of the variables, and we'll call that new matrix the mean-adjusted matrix. Therefore, it can be shown that if there are 3 variables and n rows, then our X transpose adjusted times X adjusted will give the numerators of the omega matrix that we've just shown a while ago. And if we divide everything in the cells by n, then this actually gives the actual variance-covariance matrix. Alternatively, one can use the data analysis toolpack of Excel to compute for the covariance matrix. However, it will only provide half of the matrix, which will have to be populated by just copy-pasting the transpose onto that matrix itself, as we have to note that the matrix is always symmetric relative to the diagonal, as long as we're talking about the variance-covariance matrix. Alright, that's all that we have for now. Please like and subscribe to our channel to help support us. Bye for now.